All right, so welcome to lecture 2, where we're going to talk about models and make a taxonomy of the problem space. So at the end of this lecture, hopefully we'll know about what different types of topologies and topology designs exist. And we're also going to learn about the first model for a static demand-aware network, and also first model for a dynamic self-adjusting demand-aware network. And we learn about the benefits of demand-aware approach in this context, and in the end also have an overview of the problem space. All right, so one classification you can make of the topology design space is first static versus dynamic. So this is here on the y-axis, and the second classification axis is whether the network is demand oblivious or whether it's demand aware. So that's the two actually independent dimensions. So for each of these corners, there is a possible design justification. So on the lower left, we have a demand oblivious static network. So we call this S-obl, static oblivious. Then in the upper left, we have demand oblivious but dynamic networks, so we call this D-obl. And then we have dynamic demand aware and static demand aware networks. So these are four possible design choices. And let's start with the static designs, and in particular the static demand aware networks. Okay, so let's start with the most fundamental metric that we want to consider in this design space of a static demand-aware network, and it's called the expected path length. And for that, we consider a demand matrix, D, that describes how much two nodes U and V communicate with each other. This is described by PUV. And then the distance in the designed network N between U and V. So we have the distance weighted by the amount of communication between this pair. And for example, the distance could be shortest path, but it could be anything else as well. So the expected path length is somehow describing the average distance traveled per bit. And it's the most fundamental metric, but it also relates, for example, to throughput and bandwidth tags and other important metrics that we will see later in the lecture. So more formally, the input to this static demand-aware network design problem is a communication distribution, D. We describe it with the probability between U and V. And a matrix, a maximum degree delta, that is the topology we want to design, should not have a degree larger than delta. So we want to choose the topology from that family of topologies N delta. And the output is a static demand-aware network N from this family, so that the expected path length is minimized. So we want to choose a network N from this set of possible topologies that minimize the sum of the weighted distance in this designed network N. And we'll be a little bit sloppy here. So here, basically the BND, the bounded network design problem, we refer both to the network and also to the optimal value that we can achieve in this context. So here we use minimum, but actually you could also think of it like argmin if you want to get the actual network. So let's look at an example. So here we have a demand matrix D that gives the joint distribution, and we have a set of nodes, 1, 2, 3, up to N. So this could be like computers, there could be racks, there could be peers in a peer-to-peer network. And each entry here describes how much node U communicates to node V. And we can interpret this as a joint probability distribution PUV, that the sum over this demand matrix actually equals 1. And you can also think of this demand matrix as a demand graph. So here the representation of a graph is basically the thickness of the line corresponds to the amount of communication in this demand matrix. The output in this problem is a network. So we want to design a demand-aware network N. And N should belong to this family of graphs that we have. And for example, we want to have regular graphs that have a bounded degree delta. And we want to find this demand-aware network that minimizes the expected path length as defined before. So here at the bottom, for example, if you have the demand matrix like that, the demand-aware network of bounded degree, in this case delta equals 3, could look like that. So this is what we call the bounded S-then design problem. And let's look at an example. So if we have this demand matrix on the left, then why would this be now an optimal demand-aware network? For example, here, node 4 communicates a lot to node 5. So not surprisingly, in the demand-aware network, we'll have a link there. Node 1 actually is not directly connected to 7, although they communicate a lot, but since the degree is bounded, some of the communication need to be indirect, so this can also make sense. And there can also be pairs of nodes that don't communicate, and they are still connected. For example, 4 to 6 is a good indirect link that can be used by many other pairs, so it still makes sense to add this communication link in the demand-aware network. So now you may wonder, how much can we actually benefit by designing such demand-aware networks? All right, so now let's look at the potential benefit we can have in designing demand-aware networks. And we actually will see that it can be much better to have a demand-aware network compared to having a demand-oblivious network. And here we have a simple example. So let's assume the demand graph is a two-dimensional grid on the left. So this is the demand. And let's say we want to build a demand-oblivious network for this demand. So a good choice here, if you want to make a demand-oblivious network, or almost optimal choice, is like you can have an expander graph. So if you have an expander graph of bounded degree 4 for this demand, however, what will be the expected path length? It will be log n. So n is the number of nodes, remember. So in an oblivious embedding of a two-dimensional grid, this demand graph, on a constant degree expander, unfortunately, the expected path length will be log n. Okay, so it's not a very good choice. So what can we do, however, if we have a demand-aware network of degree delta equals 4? Of course, that in this case will be very easy to optimize, because the demand graph is already a graph of degree 4. So we could simply have the demand graph be the demand-aware network. So what will be the expected path length? In this case, it will be 1, right? Because each pair that communicates will be directly neighboring in this demand-aware graph. We can have another example where we see the potential benefit of demand-aware networks. So let's say we have a graph like this, a demand graph here on the left, that is very skewed. So a pair of nodes communicates a lot, but then another pair less and less, and there's some, let's say, an exponential distribution of the frequency at which these nodes communicate. So it's a very skewed demand, all coming from a single source. So again, if you want to build a demand-oblivious network for embedding this demand, then, for example, again, an expander graph, the expected path length in a constant degree expander will be again log n. Okay, so how could I build a demand-aware network of constant degree for this type of demand? And again, let's do a degree-free network, for example, a binary tree. So one good solution here would be we have this source that communicates with all the other nodes, and we put it at the root. And then we take the neighbors of that root to be the ones that communicate most in the demand graph on the left. And then we take, again, the nodes to be neighbors that communicate less. So basically going down in the hierarchy of this tree, we have the nodes that communicate less and less with the source. So the most frequent communication partners will be very close, and so we have an optimized tree towards this demand. And if the demand is really skewed, then the expected path length of this network design can again be constant. So again, this will be a much better solution than a demand oblivious expander graph that is having an expected path length of log n. So going back to this spectrum that we designed of possible topologies, now we have a good understanding of the static demand-aware networks. But what about dynamic demand-aware networks? So what could be, what is the problem there? And here the input is not a demand matrix, a static demand matrix, but it's like a communication sequence. Okay, so you may have pairs of racks, for example, that communicate over time, so here from the top to the bottom. And each entry in the sequence is like one communication request. So for example, source rack 1 communicates to source rack to destination rack 2. And we have an amount of communication that can happen between each of these pairs. So we can describe this as a sequence sigma, where we have like S0, a source 0 communicating destination 0, source 1 communicating destination 1, etc. And the sequence may either be given offline, so maybe you know the sequence ahead of time, so there are now different choices or design options, or the sequence may be revealed over time. So in an online setting, this sequence is not known ahead of time, and then the sequence is revealed over time. And the output to this dynamic demand-aware design problem is a sequence of demand-aware networks, N1, N2, N3, etc., where each of these demand-aware networks belongs to a certain graph family. Again, for example, the regular graphs of bounded degree, or in general bounded degree networks. And the goal is twofold now. So now we have a dynamic setting. So again, we want to minimize the service cost, so kind of the routing cost or communication cost. In this case, we look at the request and the specific network on which it is served. And then we, for example, take the distance on that network, or any kind of service cost on the corresponding network, like energy related and other types of metrics could matter there. But for now, most of the time, we assume like a shortest path routing on this network N. But then we also have something like a reconfiguration cost. So now we want to change the network from this type of network Ni to maybe a network Ni plus 1 at a certain time. So we also have this adjustment cost that is like the sum of adjustments over time. And again, a basic way to measure adjustment cost would be the number of links that we change. But any other type of adjustment may also be modeled. For example, adjustments may cost energy, they may cost time, so we may also be able to model this kind of adjustment costs. So overall, the network sequence that we want to design is basically aiming to minimize this service cost over time plus the adjustment cost over time. Okay, so the natural objective here is that we have the sum of the service cost and the adjustment cost over time that we want to minimize. So the overall cost of these two components is something that we want to consider in the dynamic case. Sometimes we are also interested in the competitive ratio. So the competitive ratio is a measure to see like how much worse is an online algorithm compared to optimal offline algorithm that knows the sequence sigma ahead of time. So in case the sequence or the demand is not known ahead of time, we can measure somehow how good is this online algorithm compared to an offline algorithm. So here the cost on means the sum of the costs of the online algorithm, and the cost off means the cost of the offline algorithm, and typically we assume here the optimal offline algorithm. And again, the cost here is just the sum of the serving cost and the adjustment cost. So now we kind of get a trade-off here in this dynamic demand-aware network design, because either we reconfigure very seldom. That will be very good to save adjustment costs, but maybe if the demand changes quickly over time, we have quite a high service cost in this case. And if we reconfigure the network very frequently, then it may be very good to adapt towards the service, towards the demand that changes over time. So we have a good service cost, but we have a high reconfiguration cost. So basically, we can have a whole spectrum now of different problems. So already for demand oblivious case, we may have a setting where we have a static topology we want to design, or we have a dynamic topology we want to design. And actually, we see later in the course also a way to optimize demand oblivious networks in a dynamic manner. More interestingly, in the demand aware topology case, we also have the possibility to reason about static networks that are optimized towards the demand. And here the input could be different, right? It could be like a demand matrix. It could be arbitrary sequence as well. From the sequence, we could, again, of course, compute some kind of demand matrix. Or it could be a generator type of input, like a model where, for example, we sample from a demand matrix in an IID manner. And then we can have algorithms that are like static algorithms optimized to the different models, or an algorithm optimized to a generator model. So then we have a different type of problems. And again, of course, we have this whole world of dynamic network optimization. So we could have a setting where the input is offline. For example, imagine a machine learning application where we have a lot of repetitive learning tasks. And in this case, maybe the communication pattern, or in a MapReduce context, for example, we may have quite a predictable input that basically we can count on. And we can design a network that is optimized towards this offline demand sequence. And we could also have the other extreme, where like the input is not known at all ahead of time. And the online algorithm is completely agnostic to the future, so it needs to kind of adapt in a dynamic manner in an online fashion. And there are different, of course, models also between. So we may have a partial offline, partial online. So some of the pattern may be known, others not. So there is a whole spectrum of possible problems here. How do we evaluate these online algorithms? So one property that is very important and often considered in the literature, that we also see more later, is static optimality. So static optimality, we'll discuss it in a second what it is. And there is something called dynamic optimality. That's a different property. It's even a stronger type of property you want to have in an online algorithm. So what is a static optimality? So what we want to achieve there is that the algorithm is not worse than a static solution. So even though the online algorithm doesn't know the future ahead of time, and the static algorithm is optimized towards the demand, you want it not to be worse, the online algorithm not to be worse than the static optimal. So we call this a competitive ratio. So we compare the cost of the online algorithm that is not knowing the future divided by the cost of the static algorithm that is optimized towards the sequence, but it cannot change the topology. And static optimality means we are just a constant factor, at most a constant factor worse than the static optimal. Then another important property is dynamic optimality. So here we don't compare the online algorithm to a static solution, but we compare it to the optimal offline solution that knows the entire sequence ahead of time. So here the ratio, the competitive ratio, is between the cost of on divided by the cost of off, which is the optimal offline. And we say the algorithm is dynamically optimal if the ratio, the competitive ratio, is at most a constant. So we are at most a constant worse than the optimal offline, which of course is a very strong property. If we can achieve that, it means that we don't pay a price for not knowing the future. So basically the online algorithm, even though it doesn't know the future, is almost as good as the optimal offline algorithm that knows the complete demand ahead of time. All right, so in this course we will need a couple of important definitions, and one of them is entropy. As we will see, actually, for example, the expected path length you can achieve in a network is related to the entropy. So What is the entropy? We are given a probability distribution or a random variable x, and then the entropy is defined as the sum of the probability of these values xi times the logarithm, the binary logarithm of 1 over this probability of xi. And the probability could be, or px could be the probability, but it could also be, for example, the frequency if we talk about empirical entropy. But for now, let's look at this probability model. And another important concept that we will need is the conditional entropy. So this is like the average uncertainty of a random variable x given a random variable y. And for example, it could be, or the way we will use it in the class is that x, for example, could be the sources and y could be the destinations, or the other way around. So we want to know like what's the uncertainty about the destinations given the sources, for example, or the other way around. And we will write this entropy hx given y. And again, this is computed as the sum of this joint probability distribution between x and y times the logarithm, again the binary logarithm, 1 divided by the conditional probability xi given yi. And there is very important results that we will build upon in this course. And one is by Kurt Mehlhorn, who was studying optimal binary search trees or biased binary search trees. These are like trees that binary trees where important or frequently accessed elements are close to the root. And he actually showed, it's well known that the expected path length or the access time that you can have in such a biased or optimized binary search tree is proportional to the entropy of the probability distribution P. In the context of coding, so this is in the context of data structures, in the context of coding there is something called Huffman coding that optimizes the basically code length or the optimal or the expected code length of a certain probability distribution, so that you want to communicate the minimal amount or need the minimal amount of bits to communicate a certain text between two nodes. So there's a tight relationship between these optimized binary search trees and this coding. Often in the coding you also have the binary trees, and there typically the binary trees are prefix free, so you're communicating the letters of the alphabet in a binary form that is like a prefix free code, and I will show you in a second an example of that. And again, also in the Huffman coding, the expected length of the transmission or the expected code length is like related to the entropy, similar to the access cost in the binary search tree. So what is Huffman coding? So basically it's a dynamic algorithm that allow you to compute the optimal code for a given probability distribution. So here on the left is an example of a probability distribution where all the keys 1, 2, 3, 4 have the same probability, 1 over 4. And then the Huffman code will simply make a balanced tree where all the keys are at the leaves, because it's a very uniform distribution. If the distribution is more skewed, then the Huffman tree will look something like on the right, where the element, in this case it is 1, that is most frequently communicated or appears most frequently in the distribution is very close to the root. And then the less frequent elements or keys, they are kind of lower in the tree. So the Huffman algorithm basically builds a tree that is optimizing the expected path length. And again, you can basically show that the code is optimal if it's, or the code that is generated is proportional to the entropy of the probability distribution. So there's really an interesting connection between this coding and data structures, and also to what we want to do. So if you look at traditional binary search trees, then typically you want to have like a balanced tree, right, where the depth of the tree is never more than like log n. But then you can have something like a demand-aware binary search tree or a biased binary search tree, where the location of the keys in the tree is kind of optimized towards the probability distribution. And you may have something like a self-adjusting binary search tree that adapts to the distribution in a dynamic manner. And the more adaptive, the more demand-aware you make your tree, the better is the access cost typically. Okay, so the more you go to the right, the better is the performance of the binary search tree, because it's more aware of the distribution. And very similarly, this is the case also in coding. So if you have a worst case coding, then typically the number of bits that you need per ladder is like logarithmic. And then you have something like Huffman coding, where you optimize the code towards the distribution. And you also have something like dynamic Huffman coding, where you even adapt the code over time. And for example, if you change a language, or if you have a different frequency distribution over time for other reasons, then dynamic Huffman coding is able to adapt the code also accordingly. And then the more to the right, you get shorter and shorter codes and more efficient communication. And very similarly, we have the vision, or in this class, what we will consider is that networks become more and more demand aware. So hopefully the route length or the performance or the congestion will be optimized more and more to the right, so the more dynamic you make your network. And in fact, this is not just an analogy, but it's actually the case that you can generalize the methodology from coding and data structures also to the network. So a lot of the bounds, a lot of the algorithms that we have in coding in data structures, we will see that we can also generalize them to the network case, and have like demand-aware networks that perform better if they are more adaptive. So for example, if you have a demand oblivious binary search tree, then the expected cost there is log n. If you have a demand-aware binary search tree, then the access cost is proportional to the entropy. And if you make it dynamic, you may even want to achieve something like the entropy rate over time. So this is something that is a metric that could be for a dynamic setting. And very similarly, as we will see in the next lecture, we could also have similar bounds in the context of demand-aware networks. So the more we go to the right, the better and better is the route length. All right, so that's all for today. So hopefully you learned about what different types of topology designs exist, these two dimensions that we saw. We also learned about the first model for static demand-aware networks, a first model about dynamic demand-aware networks, and we also discussed the benefits that can be quite large if you make your network demand-aware. And we also saw the design spectrum, so there's actually quite a lot of different models to consider. All right, that's all for today. Thank you.